So we have problem statement for binomial distribution. Around 80% of all the visitors to La Vista Museum end up buying souvenir from the souvenir shop at the museum, and on the coming Sunday, if a random sample of 10 visitors is picked, so find the probability that every visitor will end up buying from the that particular shop, and find the probability that a maximum of 7 visitors will buy uh, souvenirs from that particular shop, right? So let's check first whether we satisfy the assumption of the binomial distribution, because that is very important before solving any statement with any particular method. We need to check that whether it is fitting and meeting all the condition for that algorithm. So what we have is there are only two possible outcomes, that is success or failure for each trial. Yes, that is a visitor will buy souvenirs from the souvenir shop or not. Okay, so the answer is yes or no. And second thing is a number of trials, that is let's say n is fixed, that it is telling that there are 10 visitors in the sample. Okay, so each trial is independent of the other trials. It is reasonable to assume that the buying activity of visitor is independent. So the last thing is we will confirm that the probability of success is the same for each trial, right? So the probability of success for each trial here is 0.8. So let's import the libraries that required. First is pandas as PD and numpy as np. Okay, for all the array, and pandas for manipulating data and to do analysis. Then we have matplot.pyplot as plt to plot all those visualization, and cborn again a library for visualization. And here we are importing stats, which is in SciPy. So the library basically contain a large number of probability distributions, as well as growing library of statistical functions. Okay, so this is nothing but the same that the stat. So here for this particular question, we first finding the z score, right? Or we can say the z score. So 0.28 is nothing but actually I have done some tests about this, right? And this is the problem statement that we solve is here. So let's estimate the probability distribution of visitors. So here we have given that n is our 10, because we have to declare the sample size in variable n, which represent the number of visitors selected randomly. So how much that number? It is 10. Next thing we have is the declare p, which represent the probability of success. So the probability that a visitor will end up buying a souvenir, p is 0.80%, right? So this is nothing but the 80%, right? Now what we have is we have to declare different possible number of visitors selected in a numpy array, because as we have defined n is 10, which is a random number. So the sample size will be our a range of 0 to 11, where we have an array of 10 numbers. Now the probability function of binomial distribution provide the probability for x number of successes from a trial, where p is the probability of success. So here we have the formula, that is you can check out this, where the n number of visitor is selected randomly. Okay, so there we will get our n for here and here. Now p, the probability of success. So the probability that a visitor will end up buying a souvenir is 80%, that is 0.8, right? And the q is nothing but probability of failure. So here what we will do is we will subtract this 80% with our 100%. So it will be 1 minus 0.8, which will give us 0.2%. So 2% chances, or we can say 20% or 0.2 is the probability of failure, where the number of successes is 10 again. Now we will use a binom.pmf, right? So the PMF, that is the probability mass function, to calculate the probability function, which provides the probability for the number of visitor So out of n equal to 10, that will end up buying souvenir from a souvenir shop. So again, to get that binom, it is in scipy.stats we will get binom. Okay, and the binomial will be our binom dot the probability mass function, where k is also given, n is also given, p is also given. So k and p are nothing but the parameter that the PMF will accept. Okay, so if we check the binomial, here you can see that this is the binomial value that we got after applying the binomial function. And as here you can see that it is array of possibility of the different number of success, right? So let's visualize these numbers. Now we are plotting this into a bar plot, right? So here we are again giving that this is plot a bar plot for k and binom. Okay, then title is this, right? And x label will be this and y label will be this. Okay, and if we show that, it will return that binomial function. And you can see that the last element of this binomial array represent the probability when the number of success is 10. Okay, and which means that all 10 visitor out of 10 selected randomly so will buy souvenir from the souvenir shop. Okay, so if we get the 10th, that is binomial of 10, so we will definitely get that the number of success. Okay, so these will buy souvenir from the souvenir shop, and this probability shows that probability of exactly 10 success, right? And now we are interested in knowing the probability of at most 7 success, which you can see that it is asking in second question, right? Find the probability that a maximum of 7 visitor will buy souvenir from that particular shop. So what we will do is, here we need to calculate probability that is x less than equals to 7. Okay, so the cumulative density function is used to calculate the cumulative probability that we have seen in our previous example for binomial distribution. Here the CDF of a random variable x is the probability that x will take the value less than or equal to x, and it can be represented mathematically as this. So this will become our formula where fx of x. Now what we will do is, we will plot the bar plot again for the probability distribution, and we are plotting the distribution here to better visualize the calculation. Of course, we do not need to create the following visualization to answer the above question, but it is just because we want to make it more clear. Okay, so you can directly use the CDF function for the probability calculation. Here we are telling that in the bar L, just take the PLT bar plot. Okay, and we want again on k and binomial. Title we have defined, font size we have given, x label and y label is that. But now the main thing is here, for I in range 0 of 8. So if bar L of I, okay, so let's say if I is 0, so bar L of 0, so at the 0 set color R, right? So here we are giving the color, the bar in red, where number of successes is less than 8. So here you can see that if it is less than 8, so it is red, otherwise it is bluish. So in the above graph, the red region represent or this value, that is x is less than equals to 7, that means less than 8. Let's calculate the probability that out of 10 randomly selected visitor, a maximum of 7 will buy souvenir from the souvenir shop. Then we will again use the binomial.cdf function for this. So again we will give the k here, now this time is 7, and we have defined above and p as well. So this is the CDF for our value less than equals to 7, right? Now if we conclude it, so there is a 10.74% chance that every visitor will end up buying souvenir from the souvenir shop, because we got it here, right? 10.73%, and 32.22% chance that a maximum of 7 visitor out of 10 will buy souvenir from the souvenir shop. So let's try to change the probability of success and probability that each visitor will buy souvenir from the souvenir shop. So to different values like 60%, 70%, like that, and visualize how the shape of distribution changes. So again we are getting the figure to plot, and here we are subplotting it. If we tell that it is binomial 7, so just take p value 0.7 and get the PMF function, right? And here we will plot the bar for that binomial 7, right? Similarly, if we check for binomial 8, that is 80%, so here we will say that p is 0.8 and plot the bar for that as well. If we tell 90%, so it will get the 90% for that binomial function, and we will plot that. So here you can see that for this is for 70%, 80% and 90%. So the number of success, you can see that how it is different in each percentage value. So it is clear that from these plot the shape of distribution changes as the value of probability of success changes. That is nothing but the p value changes. Now let's move forward with the continuous uniform distribution, or CUD. So again, let's take with an example. So the problem statement tells that IT industry record the amount of time a software engineer need to fix a bug in the initial phase of software development in this particular CSV, right? That I'll provide in the description. And where x is time needed to fix bug and x is a continuous random variable. So let's see the distribution of x and answer the below question. First, it is asking that find the probability that random selected software debugging require less than 3 hours. Okay, and next, find the probability that a randomly selected software debugging requires more than 2 hours, and find the 50th percentile of the software debugging time. So here you can see that as it is becoming our continuous problem statement. So we are getting that debugging CSV in a debugging variable. If we check the head, so this is the bug ID and this is the time taken to fix that bug. So let's plot the histogram of data along with the PDF of uniform distribution using the parameters minimum time required and maximum time required for bug fixing. So visualize the distribution of the time needed for bug fixing. Here we are plotting a one histogram, right? Time taken for to fix that bug. Okay, and here we are giving the x horizontal line, that is our this line, you can see that, and it will get an average time. Okay, so here you can see that this is the time we can consider that it will take to fix that bug. Now another way to recognize a uniform distribution in your data is to look at density plot. Okay, we will use this plot of a Seaborn library to visualize the distribution of time needed to fix that bug. So if we go for density plot for time taken to fix that bug, so sns.displot, here you can see that we are getting debugging and the column that is time taken to fix the bug. So the KDE here will be true, so we will get the plot show here. So plt.show will give that particular graph in front of us, and it is showing that time taken to fix that bug and count at which count it get resolved. So if we talk about insight, as you can see from the above plot, that all the values between 1 and 5 are having almost equal probability. Okay, so we are going to use continuous uniform distribution CUD, and we need to decide the endpoint. Like here endpoint are 1 and 5. So if we get that uniform, again we will get it from the scipy stat. Okay, and use the uniform as .pmf function to generate the probability distribution. So in X we are getting np dot line space, that is this 1 to 5, and which is for so where X equals to n, we are getting np dot line space 1 to 5 are endpoint for the 50th percentile. And if we get the props, so probability, so here uniform dot probability density function X will be passed here, log we are giving, and scale value we are giving it 4, right? So now it is asking that find the probability that a random selected software debugging require maximum time of 3 hours. So again, of a CDF of a random variable X is the probability that X will take the value less than or equal to X, right? So it can be represented mathematically as below. So Fx will be this, right? So the probability distribution, again we are plotting the same. So this is nothing but we are plotting for this x1 and those probability that we got. So here you can see that this is the time required for bug fixing and this is the probability. Okay, so how we distributed them with different color from 1 to 3 and from 3 to 5. So in the above graphs, the red region represent that is X is less than equals to 3 or less than 4. So let's calculate the probability that randomly selected software debugging require maximum time of 3 hours. So we will use uniform.cdf. So if X is over 3, again log we are giving from 1 and scale value up to 4. So it will give that the 5%. So this is the maximum debugging required for a maximum time of 3 hours. Next thing it is asking find the probability that a random selected software bug fixing require more than 2 hours. So in this case X will be our greater than 2. Okay, now we are giving the 2 to 5, all right, and 20 as our maximum limit, right? So here again we are plotting the same thing, and now you can see that the red region, this is X is greater than 2, right? From this we will calculate the probability that a random selected software debugging require more than 2 hours. So again in that case we are passing X equals to 2 from log 1 to 4, okay, and from log 1, and the scale value is R4, and to get that we are again subtracting it from 1 because we will get it from the 100%, so it will give us nearly 75%. Now let's calculate the 50th percentile of software debugging time. Again to get that 50th percentage we will pass the 0.5 for Q value, log will be our 1 and scale will be our 4. Now you can see here we are using PPF, so it will basically return the percentile point probability, right? And it works opposite of our CDF function. So if we conclude this, there is 50% chance that a randomly selected software debugging require less than 3 hours, 75% chance that a randomly selected software debugging require more than 2 hours, and 50th percentile of this software debugging time is 3 hours, right? So if we talk about the normal distribution, right, next we have this normal distribution, and here we have again a problem statement that testing agency wants to analyze the complexity of set exam, right, in that particular year, and they have collected the set score of 1000 student in this particular CSP. So answer some of the questions that will help to decide the complexity of set exam. So calculate the probability that a student will score less than 800 in set exam. Now let's first read the data set, that is setscore.csv. Okay, here it is giving one error, no such file directly. Okay, that is not found, but yeah, it is there, I'll provide in the description. Now we are calculating the mean and standard deviation parameter of the set score. So again we are using norm function. So to estimate the mean and standard deviation of the set score data, what we will do is we will get the mean and standard deviation, that is mu and sigma, and the estimated mean will be our round of anything, that is mu value is important, and the estimate standard deviation is our sigma. So we are rounding up to place. Now plotting the distribution, so it will help us to analyze the shape of the data and visualize the probability density function of that normal distribution using the parameter mean mu and standard deviation of sigma from the data. So we are calculating the PDF and PDF of set score using norm.pdf, right? So we get the density as our data frame, and density x will be our np.line space. So the value is distributed as minimum of score and maximum of score, right? So here what we are doing is we are creating an array of these 100 number in between the min and the maximum score, and store it in the first column of our empty data frame, that is x, right? So now what we are doing is, again we have density of PDF. We are telling that calculate the PDF of the created number and that is created in x, and store it in another column, that is our PDF, right? Here we have a figure and axis to plot that particular subplot. Now it is telling that cns dot hist plot, we are telling that st dot score, right? So here what it will do is it will plot the distribution of that data, okay, using that histogram. And now next we will plot the PDF of the normal distribution here, and finally giving a title and displaying the plot. So you can run and try this code, so it will definitely run and give the plot, right? Here I'm getting the error because the whole data need to be run again, so it is not finding any set score for my case. Anyway, that is not a big issue. Hope you will do that. So what the insight is here, so the main aim is to get to understand this. So as you can see in the our plot, there are two curves, red and blue. So unless and until we don't get that curve, so let's run it. Okay, what I'll do is I'll tell this run all over. So as I run this, so this is the plot that we got, and if we talk about this, so here you can see that from here we definitely get the probability or we can say the estimated mean and estimated standard deviation. Now from this plot there are two curves, right? You can see that one is red and one is a bluish, and what here is happening, blue curve represent the shape of our data distribution and the red curve represent our probability density function. Okay, so here it is telling that this data is approximately normal. Here you can see that it is giving us a normal V-shaped curve, so it is our normally distributed, and thus we can assume this data distribution to be normal and perform our calculation based on normal distribution. Now it is telling that calculate the probability that a student will score less than 800 in set exam. So if we run that, here you can see that we are again finding the cumulative probability here, which is in using norm.cdf, which calculate this probability, and less than 800, that means norm.cdf passing 800 mu and sigma that we defined above. Now it is printing that the probability that a student will score less than 800. So this is the probability that we will get, right? Now it is telling that to plot that probability distribution. Again we will plot all those distributions, so you can see that what we are getting here is again that plotting the PDF of normal distribution. Then we are telling that draw a red vertical line at this x 800. Okay, so from 0 to 800 it will draw a red vertical line. Okay, now create an array of this 50 numbers between that set score and this 800. So it will create that array and fill the specified region with the red color that we got here, right? So here the x label, y label we have given, and this is the normal distribution. Now to calculate the probability that a student will score more than 1300 in that exam, so again instead of passing 800 we will pass here 1300. But here the main difference is, you can see that in this we are doing just 1 minus normal distribution, because it is the value that is more than 1300, right? But it is the value that is less than 800. So just because it is going to be more than, so what we will do is we will subtract it from our maximum, that is 100%, right? So from 1 minus normal CDF we will pass the 1300, and again that probability that the student will get more than 1300. So this is the 0.07. Okay, if we again plot the same for that, what we will get is this is here. So if it is less than, then the plot will be here. Okay, and if it is less greater than, the plot will be at the maximum site. So it is obvious. Now to calculate the maximum marks a student must score in order to be in the 90th percentile. Okay, to get at 90th percentile again, which is we will pass the normal PPF. All right, so to calculate the 90th percentile using that particular PPF or the percentile point, so we are passing 90th mu and sigma value, so it will give that 90th percentile. If we plot for this 90th percentile, so you can see that this is where the in between values we can say. Now calculate the maximum marks a student must score in order to be in top 5%. So again, to be in top 5%, so first we will get that 95th values. Okay, and which will return the minimum score to be in 5% should be this, because the 95% will be our higher value here. So the minimum score is 1344, or we can say that to be in top 5 it should be 1344. If we plot that, so again you can see that the normal distribution for this value. Now if we conclude the whole statement, so only 15.51% of the student will score below 800 and 7.62% of the student will score above 1300. So it shows that the 2020 set exam complexity is moderate, right? So the student should score at least 1269 to be in a 90th percentile. Okay, and all those students should score at least 1344 to be in top 5%. Now if we talk about one assumption, that is standardization of normal variable. So what happens, suppose we know that the set score are normally distributed with mean of 1000 and standard deviation of 200, and ACT score are normally distributed with mean of 20 and standard deviation 5 respectively. So a college provides admission only on the basis of set and ACT score. So the college admin decide to give the top performer fellowship also, okay, to the student who has performed the best among all applicants, and the highest score received from applicant who appeared for set is 1350, and the highest score received from applicant who received for ACT is 30, right? So we need to have the college to choose the best candidate for the fellowship. Okay, so what it will give us that the plot, we will plot the two distributions for set and ACT score. So this is the plot from the normally distributed, and this is the normally distribution for ACT score. So here you can see that we will get the value for both, right? And what here is happening in this plot, the blue curve represent the distribution of set score and the red represent the ACT score, right? So the highest score of the applicant in set and ACT exam are dotted. So here you can see that with this green line. However, it is difficult for us to compare the raw highest score in the above plot, right? So thus we need to standardize the two score and compare their z-score. So this is why the standardization is required, just because to compare the raw higher score. So to find the z-score of highest score in set among all the applicants, we have the top set, right, which is 1350, minus mean value divided by standard deviation. Similarly, we will do for top ACT. Okay, so this is what the G score for highest score in set among all the applicants is 1.75, and for ACT it is 2.0. So if we plot for this together, you can see that what we will get is, again, for set we will get this green dotted, and for ACT we have this black for G score to the normal distribution. Now in the plot, again it is telling that the line represent the standardized higher set score of the applicant. So it is nothing but 1.75 standard deviation above, right? And the mean with the black line represent the standardized higher ACT score of the applicant, which is 2 standard deviation above the mean. Okay, so here you can assume that. Now the mean means that among the applicant, the highest scorer in ACT performed better than the highest score in set. Okay, so ACT is a higher performer than the set, and thus the top performer fellowship should be given to applicant who has scored highest in the ACT. So this is how we will get the conclusion for that whole study. Yeah, thanks.